Okay, guys, good thing I took a break there because, man, time just flies when you're doing these things. I thought it was maybe at like 10, 15 minutes. I am going to try and keep them shorter, but I mean, you can understand, like, if it's going to take what it's going to take. Anyways, I'll try to move things along here. So, another bonus. I kind of changed what I was going to do. I started to do it using the contrapositive, and I realized I'm just making it more convoluted than it needs to be. So what were we doing? We were trying to show that the independent set problem reduces to the vertex cover problem. Well, how are we going to do that? Well, we had this theorem that we were trying to prove, and that said there exists in G a vertex cover of size the magnitude of V minus K if and only if there exists an independent set in G of size K. And I was able to show that, okay, if there's a vertex cover of size V minus K, well, that implies there's an independent set of size K, but in order for the reduction to work, I need this to go both ways. I need this to be an if and only if. So in order to finish this off, I'm going to try to prove that if there's an independent set of size K, then there's going to be a vertex cover of size V minus K. So what are we going to do? Well, assume we have an independent set of size K. Assume I is an independent set of size K in G. Okay, what are we going to do from here? Well, let's consider V minus I. Now, first thing, very similar to last time, what's the magnitude of V minus I? What's the cardinality of V minus I? Well, it's just going to be, of course, the magnitude of V minus the magnitude of I. What's the cardinality of I? It's K. It says right there. So, just as an aside, the magnitude of V minus I equals magnitude of V minus K. Well, I mean, that's good news to start off because we're trying to show that there's a vertex cover of size V minus K, but we still need to show this thing's a vertex cover. We don't know if it is or not. It's going to be very similar to what we did before. Consider any edge in E, and I'll call that edge V1. So this is just shows you how much logic I do. My E's have become backwards E's. This should be a non-backwards E for the set of edges. Consider any edge in E, and I'm going to call that edge V1, V2. Okay. What can I say about this edge? Then I know it is not the case that V1 is an element of I and V2 is an element of I. Where did I get that logic? Well, consider if they were. Imagine if V1 and V2 were both nodes or vertices in I. Well, we know the edge V1, V2 is in the graph. What does that mean? That means V1 and V2 are directly connected. Well, if V1 and V2 are directly connected and V1 and V2 are both in I, well, that means I isn't an independent set, does it? Right? But I is an independent set, so we know that cannot be the case. Okay. Therefore, V1 or V2 are in the set V minus I. So it could be the case that one of them, just one, V1 or V2 is in there, or both are both in there. But that's going to be true about every edge. Well, if I have V1 or V2 in this set, what does that mean? That means V minus I is a vertex covered. I mean, you can logic that out intuitively and kind of think, well, every edge is covered. Or you can actually go back in your notes / the previous lectures and see that this is essentially the exact formal definition of what a vertex cover is. Therefore, V minus I is a vertex cover. So this was actually very similar to the proof that we did the other way, trying to show if there's a vertex cover, then there's an independent set. And if you have that intuition, that's good intuition. And with this problem, I was being maybe a little bit more pedantic, a little bit more explicit than I needed to be, because basically a lot of these arguments we're using in the first part, you could do an if and only if argument. But the reason I did this is just to hammer home that when you're doing a reduction, it needs to go both ways, okay? I can't have yes answers for the yes answers and then potential yes answers for the no answers. It has to be the case that there's an independent set of size k only when there's a vertex cover of size k minus 1. We can't have any overlap. It has to be a direct if and only if. Okay? Similar to the mapping reductions from before. So what does that mean? Well, we were able to prove that theorem, and you go back to the previous video, you look at the reduction, you basically have a graph. You want to know, is there an independent set of size k? Well, you ask that black box solution, is there a vertex cover in that same graph of size k minus 1? And it's going to work out. You're going to get the answer. So, what does that mean? That means independent set reduces to vertex cover. Sweet. Cool. So vertex cover is at least as hard to solve as the independent set problem. We start to build up our hierarchy of problems from here. So okay, vertex cover is at least as hard to solve as independent set. Let's see if we can come up with a problem that's at least as hard to solve as vertex cover. And you can kind of see we start building up this hierarchy within these NP problems. Okay, what's the next problem we're going to look at? It's going to be a graphing problem as well. And I know this particular lecture is heavy on the graphing problems. Not everyone likes graphing problems. I get it. It can be hard to keep track of all those edges and nodes. And it's like, well, what's the logic here exactly? But these ones honestly aren't that bad. And this next one, I'd say, is probably the most intuitive problem of the group, of the three that we're going to look at. So this next problem is the Clique, or the Clique problem. So I've heard this said both ways. It's got a Q in there, so no one's quite sure how to pronounce it. So I've heard it said Clique or Clique. I'll probably switch between the two. I don't really know which one I say. Anyways, it's like, you know, when you think of high school and you think, oh, there's cliques in high school, where you go to a certain club, there's cliques inside this club. It's essentially the same idea. What do I mean by that? Well, I'd say, given a graph, G equals VE, that's what a graph is. S is a clique, and S is going to be a subset of the vertices again. So S, subset of V, a clique's just a subset of the vertices. It's just a set of vertices in that graph. Is a clique, or a clique, whatever, if for all V1, V2 that are in that clique, it just so happens that V1, V2 is an element of the edge set, meaning for all two edges in the clique, they're directly connected. So, I mean, we could be a little bit more specific here and, you know, put in some stuff to take care of self loops and self edges. Let's just sweep all those details under the rug. Let's not worry about them. Let's not get bogged down in that stuff. So we're just saying it's a subset of edges, subset of vertices in a graph such that every single node in that subset is connected to every single other node in that subset. So let's just take a look at that graph. Let's see if I'll try to come up with an example here. Okay. it's harder to come up with small examples for the clique problem, but I hope you guys understand what's going on here. Let's put an arbitrary labeling on these things. Okay, so is the set S1? 1, 2, 3. Is that a clique? Yeah, it's a clique. Why? Well, 1's connected to 2, 1's connected to 3, and 2's connected to 3. What about the set 1, 4? No, it's not a clique because 1's not connected to 4. What about 3, 4, 5? Is 3, 4, 5 a clique? Well, you check it out. 3 is connected to 4, 4 is connected to 5, 5 is connected to 3. Yes, it's a clique. What's the largest clique in this graph? And I'm sure all of you are already there. What we call, the optimal clique, or the largest possible clique. Remember, with independent set and clique, we're trying to build the largest possible set. With vertex cover, we're trying to build the smallest possible. Okay, so the optimal clique, the largest clique in this particular graph is, of course, 3, 4, 5, 6. All right. Why is that the case? Well, you come here and you check. 3 is connected to the remaining 3 nodes in that set. 4 is connected to the remaining 3, so on and so forth. They're all connected, therefore it is a clique. And that's why it's like the same kind of clique as like in high schools. It's groups of people that kind of all hang out with each other, right? They network with each other. Doesn't mean they network with just each other, but everyone in that clique networks with everyone else in that clique. Okay. Like I said, I think it's easy to grasp, or easier to grasp what a clique is than an independent set and vertex cover. But does that mean it's an easier problem? Well, not necessarily. Just because something's easy to understand doesn't mean it's easy to solve. Lots of these problems are actually easy to describe, but very, very difficult to solve. And as an exercise for yourself, what you should do is convince yourself that the clique problem is in NP. So what do you need to do to figure out a problem in NP? Think about it. I've told you a few times before. You can take it from there. Okay. So before we get into the reductions and trying to fit clique into this hierarchy that we had, I'm going to define one more construct, okay? Given a graph G, I'll call this G bar equal, and you know what, I should be explicit with this graph here. This graph, what does it equal? It's VE. So, given a graph G, let G bar equal, and what's G bar going to equal? It's going to be the exact same set of vertices, so the exact same set of nodes as G, except it's going to have this E bar as its set of edges. What's E bar? Well, where for all edges, what's a potential edge? What's the set of, what is an edge potentially a set of? Well, it's going to be V cross V. So for all edges, V cross V, so for all two pairs of vertices, for all potential edges, we're going to say E is an element of E bar if and only if E is not an element of capital E. So you might look at that and be like, what in the world is that saying? It's not saying anything crazy. All it's saying is in G, it's the exact same set of nodes, except what? If there is an edge in G connecting two nodes, it's not going to be in G bar. And if there isn't an edge in G connecting two nodes, that edge is going to be in G bar. So, this is going to be dangerous because I'm sure I'm going to make some mistakes. And maybe I'll leave this as an exercise for you because, I'm just kind of doing this improv. What is G bar here? Well, 2 isn't connected to 5, so I'm going to have an edge there. 2 is not connected to 6, so I'm going to have an edge here. Oh man. 3 is not connected to... Oh, it is connected to 6. So look at this. 3 is connected to everything in this original graph, which means it's going to be connected to nothing in G bar. So if this is G, this is G bar. What's 1 connected to? Well, it's going to be connected to 4. It's going to be connected to 5 and 6. Oh boy. Is that it? Did I do it? Maybe. It looks completely different. I think it could be correct. Exercise for you guys. Verify this is correct. And if it isn't correct, correct it. Okay, but that's all G bar is. It's just the same graph, you know, with the edges inversed, essentially. And again, remember I said at the beginning, there might be some small details about self edges. Let's just sweep that under the rug. We don't care about it. We don't care about self edges for these problems. Okay. So that's the last piece of the puzzle. Now, given that, I want to show vertex cover reduces to clique. And I guess I should define clique in the language form, but I mean, it should be quite intuitive for you to see, especially for things, once we've seen things like vertex cover and independent set already, defining clique as a language should be straightforward. It's going to be something like this. We're going to give it a graph, and we're going to give it a number k, and it's going to be, you know, the set of all gk where there exists a clique of size k or more in G. So that's the clique problem. And we're trying to show that vertex cover reduces to clique. How do I do that? Well, I'm going to have a theorem like before. And we'll start with stating the theorem. How would we actually use that theorem to construct a reduction? Try to come up with that. And then if we can construct a reduction based off that theorem, then try to prove the theorem. Okay, what's the theorem I'm talking about? Theorem. There exists a vertex cover of size k in G if and only if in G bar there exists a clique of size v minus k. So it's actually kind of similar to that theorem we had before. And I mean, these problems, you know, we're doing reductions between them. They do relate to each other. How exactly they relate to each other, well, hopefully by the end of this lecture, we'll have a clearer idea of that. So what's going on here? Okay, well, if this is the case, if this theorem holds, how would I show that vertex cover reduces to clique? Well, it should be relatively straightforward at this point. Because in order to show that vertex cover reduces to clique, I assume I have a black box that solves the clique problem, and I can, you know, call that black box in whatever instance I want to. So the idea is, okay, given the G, and I want to know if there's a vertex cover of size k or less, well, that's going to be true if and only if in G bar there exists a clique of size v minus k or more. So I just basically have to construct G bar and then call the clique black box on G bar magnitude of v minus k, and I'm going to get my answer. And it's all going to work out. Some fine print. Remember, I have access to that black box and I can call it, but I have to make sure everything I do to change, you know, this problem instance of vertex cover to kind of look like a problem instance of the clique problem, I have to make sure I can do that in polynomial time. Can you construct G bar in polynomial time? Yeah, you can. What do you have to do? Well, you basically just loop through all the edges of G, loop through all the vertices, construct a new graph, but again, you can do that in probably quadratic time or E time. But remember, in this course, all we care about is polynomial or not polynomial. So as long as it's, big O e to the power 10 factorial, it's cool, good enough. It's polynomial time, consider it free. So yes, I can construct G bar in polynomial time. Okay, I can construct G bar in polynomial time. That means if this theorem holds, I have a reduction from vertex cover to clique by just asking the black box, does there exist a clique in G bar of size V minus K? So what I need to show is this theorem exactly. I need to show, okay, if there's a clique of size V minus K in G bar, that's going to be true if and only if there's a vertex cover of size K in G. So we have to show that both ways, but I'm going to move a little bit more streamlined through it this time than compared to the proof with the independent set and vertex cover problem. What I'm going to do here is just do like an if and only if argument through the whole thing, so we don't have to kind of break it down into cases. So here's the proof. I'm going to say S is a clique in G bar of size magnitude V minus K. Okay, so I'm assuming I have a clique in G bar of size V minus K. And hopefully I have a string of if and only ifs, and at the end of this proof, maybe it's down here, maybe it's onto the other board, but hopefully somewhere I see if and only if there exists a vertex cover of size K in G. Okay, well I'm saying S is my clique. What else might I consider here? Well, let's say this. If and only if, and remember, it's a clique in G bar. Okay. So think about this. If and only if for all V1, V2 that are elements of S. So I'm taking two vertices in my clique S. And I'm saying this is true if and only if for all of those vertices, the edge, V1, V2, and here's my question. Is this going to be an element? Is this edge going to be an element of E? Or is it not going to be an element of E? Or do we need more information? Can we say anything at all here? So take a moment, pause the vid, solve it, or reason it out, think about it. We'll come back and we'll discuss what you guys thought of. So 1, 2, 3, and we're back, okay? Well, let's consider this for a moment. Every two nodes in a clique are connected. That's the definition of a clique. So you might say, oh, well, V1 and V2, they're elements of the clique, therefore they're connected, therefore that edge has to exist. But be careful, because remember, this is a clique, not in G, but in G bar. That means, yes, these two things are connected, but they're connected in G bar, meaning what? Meaning that this edge, V1, V2, is an element of E bar, not E. Well, I'll just write this out as another step, but that's going to be true if and only if for all V1, V2 elements of S, V1, V2, I don't know why I wrote that. Oh man. I need like some shelves over here. I'll code. V1, V2 is an element, is not an element of E. Okay. Well, let's think about that. What's the implication of that? Well, that has to be true if and only if for all edges, so for all V1, V2 that are elements of E, so for all edges that are in E, if it can't be true that there's no edge here, that means that one or both V1 is an element of V minus S, or V2 is an element of V minus S. So let's just review that logic. So we knew that for all elements, or for all nodes V1, V2, the edge V1, V2 is not an element of the edge set. Okay. Well, then we can say for all edges that are in E, it has to be the case that at least one of them, could be both, but definitely at least one of them is outside the set S, meaning at least one of them is in V minus S. Because if they were both in S, that means that edge wouldn't exist. Okay, but we're just considering the edges in E. Okay, but what does that mean? Well, again, this kind of formulation here should be a little bit familiar. I think it's probably the third time we've seen it in the past few videos. It's all supposed to be the same lecture, whatever you want to call it. But that means what? Well, that's true if and only if V minus S is a vertex cover. Oh, nice. But that's not quite what I want, right? So I know if there's a clique of size magnitude V minus K, there's a vertex cover in G, but I need to know that the size of that vertex cover is at most K. Well, what's the magnitude of this? Well, this is, again, what in the world happened there? Okay, good. Whew. Okay. Just as an aside, what's the magnitude of V minus S? Well, this gets a little tricky, I know, because we have to use some tricks, but we know that's going to equal the magnitude of V minus the magnitude of S. Well, hold on. What's this up here? Did I know something about the magnitude of S? Hold up. Remember, I'm saying S is of size V minus K. Okay, that means I can sub this in. You gotta be careful with your negatives. You get this negative, that means this turns into a plus. Some advanced stuff. Hold up. Can we make some simplifications here? Yeah, look at this. Sweet. That means this set here, V minus S, that's a vertex cover. What's the size? K. And look at this. A bunch of if and only ifs the whole way, meaning that this reduction is going to work. So we know, okay, given a graph G, there's a vertex cover of size K in it, if and only if there's a clique of size V minus K in G bar. So we know this theorem holds, but that's going to be exactly the crux of what our reduction is. Because what's going to be our reduction? Well, we're going to have our black box which solves clique, whatever, and we're just going to say, okay, I need to know if there's a vertex cover of size K. Well, I'll just ask the clique problem, is there a clique in G bar of size V minus K? If there is, then there's going to be a vertex cover, and we're good to go. Okay, so what does that mean? Let's review. That means, from the previous video, or did we show it in this video? May have. We think we finished it off in this video. It's all blending together. So we know clique is at least as hard to solve as vertex cover, which is at least as hard to solve as independent set. What did I write there? What in the world is that? I don't know why I did that. Weird things, weird ways the mind works. Okay. Well, that means we have this order. So based off this, you might say, well, independent set seems to be the easiest of the three to solve. And you might be technically correct, but you just need to be careful with what you're saying there. So clique is the hardest to solve, but remember, we're saying it's at least as hard to solve as vertex cover. So what if they're all the hardest to solve? What do I mean by that? Well, what if they all have equal difficulty in terms of this polynomial reduction stuff? What do you mean? Well, what if I can show this? Well, that would mean I get something like this. Independent sets less than or equal to, essentially vertex covers less than or equal to, cliques less than or equal to independent set, but that means they're all equivalent under this polynomial reduction ordering. Okay, can I show that? Oh, maybe. Let's try. So I guess I have some room here. I guess I'll use that room before I go erasing the other board. So let me give you a theorem. There exists an independent set of size k in G if and only if there exists a clique of size k in G bar. Okay, and this G bar is the same construct that we used from before. It should be, pretty simple, or at least becoming more intuitive, more straightforward for you guys to see these theorems and then see, oh, okay, I can see how to build a reduction from that. Because if I want to know if there's an independent set of size k and G, and I have access, if I want to know there's a clique of size k in some graph G bar, you know what? Because we're doing it this way, let's just switch these two, just to make it easier. So if I want to know that there's a clique of size k in G, I just have to construct G bar, okay? And then ask my independent set black box, does there exist an independent set of size G bar in K? If it does, and this theorem holds, then I know, yes, for sure, there's a clique in G of size K. And if there isn't, I know for sure there isn't a clique of size K in G. So that's how the reduction is going to work. Okay, so now I just have to prove the theorem. Okay, assume S is a clique in G of size K. Okay, well, if that's true if and only if for all V1, V2, for all nodes that are in S, that means that edge V1, V2 is an element of E. Remember, it's a clique if they're all connected. So in order for two nodes to be in the clique, they have to be connected. Therefore, that edge, V1, V2, is in that graph G, meaning it's in the edge set of GE. Okay, well, that's of course going to be true if and only if for all V1, V2 that are in that clique S. Well, that means V1, V2 is not an element of what? It's not an element of E bar. Okay, why is that the case? Well, I mean, if that edge is in E, then it can't be an E bar. That's the definition of E bar. Well, what does that mean? Well, that's true if and only if S, let's consider S in G bar. Okay, so I take that same set of vertices in G bar. Look at any two vertices. In G, they were connected. But that means in G bar, they aren't connected. Well, what does that mean? Well, remember the definition of an independent set. You take that set of vertices, it's an independent set if you take any two vertices and they're not connected directly. There's no edge connecting them. Therefore, this is true if and only if S is an independent set. It's an independent set, not in G, but in G bar. Okay, well, we don't even have to do our complicated algebra like we did before, because we want to show that S is an independent set of size k, but S is a clique of size k and G is the same set of vertices, so the cardinality is the same. Therefore, this is an independent set of size k. Okay, that means we have this reduction. So, independent set is the same difficulty, in this polynomial reduction framework as vertex, cover, and clique, and it goes all around. It's basically like a circular set of reductions. What did we show? Well, we showed initially that independent set reduces to vertex cover, reduces to clique, which reduces to independent set. And if you were really following along and grasping everything, you may have been raising an eyebrow at some of these reductions I was showing, because if you understood the proofs and the theorems and the implications, you could have been saying, look, you could take the exact same reduction and just kind of reverse the process to show that these all reduce to each other. You could do that as well, or showing this circular structure of reduction works all the same. All we're showing is this reduces to this, therefore, they're all the same level of difficulty in this framework. Okay. I think that's enough for now, but as we'll see moving forward, this level of difficulty, you start adding more problems, more complicated problems, and you find, oh, that reduces to this, but this reduces to that, and it's also the same level of difficulty. And this problem is also the same level of difficulty as these problems. And you get all these NP problems together, and you find that a lot of them have an equivalent plateau or tier of difficulty. Is that coincidental? Well, next lecture we're going to see another class of problems. So we had P and we had NP. Next time we're going to see NP complete. If I'm getting a little bit ahead of myself, I'll catch you in the next lecture. Thank you for your attention.